Have you ever stopped to think about what it really takes to keep an entire country running? Today, we're going to do just that. We're going to unravel the UK's daily power puzzle. And believe it or not, our guide is actually data from a GCSE physics paper. So let's dive in. And here it is. This graph is basically the UK's electricity demand over a single 24-hour period. As you can see, it is not a flat line. It is a massive, dramatic rise and fall. It's a daily roller coaster that the national grid has to ride absolutely perfectly, day in and day out. All right, so let's treat this like a puzzle. What on earth is driving this huge swing in energy use? And how do we even begin to manage it? Let's start by taking a closer look at the highest point of that climb. Let's just focus for a second on the sheer scale of that peak. At around 5 p.m., the demand for electricity in the UK hits a staggering 50 times 10 to the power of 9 watts. So what does that number actually mean? Well, that's 50 gigawatts. To put that into perspective, that is enough power to boil about 50 million kettles all at the same time. I mean, imagine the national tea break that would be. It's just an incredible amount of power needed in a single moment. So the real question is, why? Why this crazy peak? And why that deep, deep valley in the early hours? Well, the answer, when you think about it, is us. It's the rhythm of our collective daily lives. And this timeline really tells the story of the day. At 4 a.m., we hit the absolute low point, while most of the country is fast asleep. Then the morning rush kicks in. Alarms go off, showers turn on, kettles are boiled, and you see demand shoot up. After a bit of a plateau during the workday, we get that massive evening peak as millions of people get home, start cooking, and switch on the TV. Then, as the night winds down, so does the demand. It's a perfect picture of how our habits create this huge national challenge. Which brings us to the next, really crucial part of this puzzle. If our demand is all over the place, how does the electricity grid possibly keep up without, just crashing? Well, the strategy is basically two-part. First, you have what are called baseload stations. Think of big nuclear or fossil fuel plants that just run constantly, day and night, providing that minimum power level we saw in the dead of night. But then, to handle those big surges, you need peak load power stations, plants that can be fired up really, really quickly. So what kind of power stations can do that? Well, we have some fast-acting renewables like hydroelectric power. And we also have more traditional, flexible sources like gas-fired stations, which can ramp up a whole lot faster than something like coal. Now, hydroelectric power is a fantastic tool for this job. It's pretty simple, really. You just open the floodgates, water rushes through the turbines, and boom, you get a massive, almost instant boost of electricity. It's perfect for that morning kettle rush. But, and this is a big but, it's not a silver bullet. The exam question points out two key limits. First, its maximum output is 1.5 gigawatts, but the total increase in demand is over 20 gigawatts. So it just can't cover that surge on its own. And second, it can only run at full power for about 5 hours before its reservoir gets too low. Think of it as a powerful sprinter, not a marathon runner. Okay, so if a giant hydroelectric dam can't plug that gap all by itself, where does the rest of that peak power come from? Well, this leads us to the changing story of the UK's fossil fuels. Over the last decade or so, there's been a truly seismic shift in how the UK generates its electricity. Specifically, we're talking about a dramatic showdown between two fossil fuels, coal and gas. And this chart right here, it tells the story perfectly. It shows electricity generation for the month of January year after year. Just look at the dark gray bars for coal and the light gray ones for gas. They are moving in completely opposite directions. Let's really simplify this just to see how stark that change is. Back in 2014, coal was king, generating over 12,000 megajoules. Fast forward to 2018, gas is the dominant one, and coal generation has absolutely plummeted by nearly 90%. It's basically a complete flip-flop in just 5 years. It's pretty incredible. So, why the big switch? Well, the physics paper points to two key environmental advantages for gas. Unlike coal, burning gas doesn't produce tons and tons of solid ash waste. And, critically, it doesn't release sulfur dioxide, which is a major cause of acid rain. So you can see why it's often seen as a cleaner fossil fuel. But this whole story about the UK's energy mix, it doesn't happen in a vacuum. It is deeply connected to the biggest challenge of our time, climate change. So we've just seen this really compelling data,
right? The UK has made this huge move away from coal, which is by far the dirtiest fossil fuel, and that is a genuinely positive step. But then we see this graph. And while one country is changing its energy habits, this chart of mean sea surface temperatures shows a very clear and pretty worrying global trend.
And the paper gives us the crucial context. It states that this isn't just about weather. A consistent change in the mean surface temperature, year after year, that is the very definition of climate change. So what's the conclusion from this data? Well, despite all the little ups and downs from year to year, the overall trajectory is just undeniable. That line is going up. The mean surface temperature of our seas is rising, and that is clear evidence that our climate is changing. The UK's daily power puzzle shows us a nation in transition, moving away from old technologies towards new ones. But that global picture is a stark reminder of just how urgent and absolutely massive this challenge really is. It leaves all of us with a really critical question to think about. As our energy story continues to unfold, what will the next chapter look like?